In this last video for 3.1, we're just going to look at special systems, right? Every chapter has this like, oh, but what about these special things? In 1.1 and 1.2, they were identities and contradictions. You had an infinite number of solutions and you had no solutions. It's going to be the same thing in 3.3, but unfortunately we have to give them entirely different names. So we are going to have two choices. You can have dependent equations, which is really just the same equation, or independent equations. Those are different equations. You can have a consistent system, means there is a solution, or an inconsistent system, which means there's no solution. So what's going to happen is we're going to look at these from a graph perspective. There's three options when you're graphing. Option number one, you're going to have these two graphs that are going to have different slopes and different y-intercepts. So the indication when graphing that you're going to have this is that when you go to graph, you have different slopes. Actually, that's it. Just different slopes. That is the only criteria. If you go to graph and your equations have different slopes, you're like, okay, it's going to look like this, right? In some form or fashion. Now, do you think these would be dependent equations or independent equations? Would they be the same equation? Could you be the same equation and graph two different lines? No. These are independent equations. Is there a solution or is there no solution? Is it consistent or inconsistent? Well, there is a solution. It's where they meet. So this would be a consistent system. Okay. What about these two? What do you notice about these two lines? They are parallel. Your indication when graphing would be that they have the same slope, but they would have different y-intercepts. I really don't think anyone ever uses my note keys because they can probably never read my writing. That was a same slope or different y-intercepts and different y-intercepts. What about these equations? Do you think they'd be different or the same? Well, they have to be different. They don't graph the same line. So these would also be independent equations. Is there a solution? Are parallel lines ever going to cross? No. So this is going to be an inconsistent system. Okay. What about this? This is surprisingly two different lines, but they graph the same line. So it's two different sets of equations, but they graph the same thing. What does that mean? Well, it means that they're dependent. They have to be the same equation. And is there a solution? Oh, there is a solution. This is a consistent system, but it's consistent all the way along. There'd be solutions all the way along. There's going to be an infinite number of solutions. How are you going to know that you have this dependent equations? Well, they're going to have the same slope and the same y-intercepts, right? They're going to be the same equation. So when you're graphing, if you get different slopes, you know that they're independent equations, they're different, and there's going to be a solution. It's consistent. If you go to graph and they have the same slope but different y-intercepts, they will be independent equations, but they're inconsistent. There's no solution. And then if you go to graph and they have the same slope and the same y-intercept, well, they're dependent equations. They're the exact same. And there'd be a solution. In fact, there'd be infinite numbers of solutions. Okay, so what's going to happen is you're going to be solving an equation by graphing, and one of these three scenarios are going to come up. Or you're going to be solving by substitution and elimination, and we have to look to see what that's going to look like. First off, before we get there, I can't forget to say this, is that we never, we don't call this guy, we don't call anything, right? We would just get a solution. Whereas these two lines, we would say that they are inconsistent. Why? Because they're the only system that had no solution. So by that standard, what do you think we would call this system? Consistent's already taken, but it's the only set of equations that are dependent. So if you get no solution, we're going to say inconsistent. If you get an infinite number of solutions, or your two equations are the same line, you're going to say it's a dependent system. Okay, so you can tell that by graphing, but we're also going to look at what happens when you're solving. So we're going to skip this next little bit, and we're going to just look at our first example. So we have this first example here. We're going to solve this system first off by graphing. Okay, so this equation is already set up as y equals negative 2x plus 6. So this is going to have a slope of negative 2 over 1, and it's going to have a y-intercept of 6. So I'm going to start by graphing a y-intercept of 6, and then I'm going to go down and right, because negative direction, positive direction. So I'm going to go down 2, right 1, 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 down 2, right 1. Because remember, when you're solving a system by graphing, you want as many points as possible because one of them is going to be the solution. If I took this equation and I wanted to graph it, I would have to solve for y first. So I'm going to add 8x to each side. I would end up with negative 4y is equal to 8x minus 24. Then to get y by itself, I'm going to divide every term by negative 4. And I get y equals 8 divided by negative 4 is negative 2. And I get negative 24 divided by negative 4, which is positive 6. This has a slope of negative 2 over 1 and a y-intercept of 6. So if you were graphing this, you'd be like, well, there's no point in graphing this again because it's the same line. So what would I call this? Well, we said if the lines are the same, they are dependent equations. So I'm going to put that these are dependent equations. I had to pause the video for a second. So what I wanted to make sure that this question said, so this is what the textbook says, is that you're going to solve each system. If the system is inconsistent or has dependent equations, you're going to say so. So for this one, I said that it was dependent because when I graphed it, they graphed the same line. If I was solving, but I wasn't doing it by graphing, how would you be able to tell that this would be these would be dependent equations? Well, let's take this one and let's solve by substitution because it's set up really nicely to do that. We would have negative 8x minus 4, and then I'm going to substitute in for y negative 2x plus 6, and then that's going to equal negative 24. Okay, so let's say I didn't want to graph and I wanted to solve by either substitution or elimination, and I chose substitution. I'm going to keep going. I get negative 8x. Now I'm going to multiply the negative 4 through. I get positive 8x minus 24 equals negative 24. What are you going to notice that happens? Well, we've got negative 8x plus 8x, which is 0x, so the x's went away. And I was left with, oh, look at that, a true statement. Because it's a true statement. So even though these are all different, chapter 1 and chapter 3, even though we're giving these different words, it all comes down to the same thing. If you're solving and the variable goes away, you're either going to be left with a true statement or a false statement. If you're left with a true statement, that means that they are dependent equations. So if you are solving and it is like this, right, you're going to end up with a true statement. Something like negative 2 equals negative 2, or 0 equals, oops, not 0 equals 2, 0 equals 0. Now, whoops, I just wrote that in the same spot, wrong spot. Sorry about that. I meant to write that here. When you're solving, you end up with a true statement, something like negative 2 equals negative 2, or 0 equals 0. What does that mean? Well, it means that you're going to say it's a dependent equations. And how many solutions are there? There's an infinite number of solutions. Now, if it asks you to state what the solutions are, here's the weird thing. You're going to say it's the solution of points, x, y, such that y equals negative 2x plus 6. It's all the points that satisfy this equation. So it's not all the points in the world. You can't say that x is everything, right? In chapter 1, if we got a true statement, we're like, x is everything. In chapter 3, we're like, okay, there's an infinite number of solutions, but they're all points on the line. All the points on the line will satisfy both equations. Okay. So that is my dependent equation scenario. The last thing we're going to look at, obviously, is my inconsistent system. So the first thing we would do is we go to graph it. So if I was to take this one and rearrange it for y, I've got 2x minus y is equal to -4. I'm going to minus 2x from each side. I end up with negative y is equal to -2x minus 4. Then I'm going to divide every term by -1. So I end up with y equals 2x plus 4. And then we go to graph it. We've got a y-intercept of 4 and a slope of up 2, right 1. Great. Or down 2, left 1. Then I take my other equation and I solve it for y. So I've got -2x plus y is equal to -6. I'm going to add 2x to each side, and I end up with y is equal to 2x minus 6. Different y-intercepts, but the same slope. So both of these equations have a slope of 2, but they're not the same line because this one has a y-intercept of -6 and this one has a y-intercept of 4. So if I was to graph the second line, I would have a y-intercept at -6, and then I'd go up 2, right 1, up 2, right 1, up 2, right 1. Now because these two lines are parallel, they're never going to meet. So that was horrible. Try to connect my dots a little better. So I can't state a solution, but I can say whether, now let's look at the wording again, because I always forget the words, right? But it's always in the question. Solve each system. Well, I couldn't. If the system is inconsistent, meaning no solutions, or has dependent equations, meaning there's an infinite number of solutions, say so. So for this one, I would say that it's an inconsistent system, meaning that there are no solutions, right? Empty set brackets. What would this look like if I was solving it? Well, this one, 2x minus y is equal to -4, and -2x plus y is equal to -6 is set up perfectly for elimination. So if I was solving this one by elimination, both of my coefficients are the same with opposite signs. So 2x plus -2x is 0. X, -1y plus y is 0y, and then -4 plus -6 is -10. I'm left with 0 equals -10. My variables went away, and I was left with a false statement. If you are left with a false statement, you're going to say that this system is inconsistent. Okay, let's go back and finish that chart. So for this one, if your lines came out parallel, you would say it's inconsistent. If you're solving and the variables go away and you're left with a false statement, something like 0 is equal to 2, then you'd say that there are no solutions. How would you, oh, sorry. I just changed these notes, so I'm not 100% used to them. So there are no solutions, which you would say as this or this. Okay, so for both of these, the variables go away. Isn't that super mathematical? The variables are eliminated, right? When you go to solve, the variables go away and you're left with either a false statement, which means there's no solutions, it's an inconsistent system, or you're left with a true statement, which means that, oh man, sorry guys, this should have been 0 equals 0. That's what happens when I film videos at 6 o'clock at night. Okay, so or you're left with a true statement, which means there's an infinite number of solutions, and it's they're dependent equations, and you would state your solution like this. I didn't talk about this one, so for this one, if you're graphing, you'll just find a point where they intersect. If you're solving, you'll get like x equals 3. The variables won't go away. How many solutions will you get? Just one, and you will state that solution as an ordered pair, x, y. Awesome. So sorry about a little bit of confusion in there, but this is your special systems and how you see it via graphing for dependent equations, how you see it graphing for inconsistent systems, and what will happen when you're solving an equation. All right, hope it makes sense.